This video is about word vectors, and it follows on from the initial high-level spam and ham classification overview video. What this video does is to look at some detailed techniques for changing how word vectors are generated. What is a word vector? It's a representation of the tokens, usually words, in a document, and these correspond to example sets in RapidMiner. Each example is a document and each attribute is a token. And it's very important to get the attribute values correct for each example in the context of the problem being solved, because variations can change the performance. What we'll look at in this video are four basic methods. These are binary term occurrence, term frequency, and term frequency inverse document frequency. What we'll then do, having looked at them in detail, is apply them to the spam and ham classifier to see what happens and try and understand what's going on. So before we go into a worked example, let's a brief explanation of some of the background. Binary and term occurrences, these are really simple. Binary term occurrence, basically if a document contains a word, the attribute for it has its value set to 1, otherwise 0. Very straightforward, you'll see that in a moment. Term occurrence, similar, this time it's simply the count of the number of times the word or the token appears. Very straightforward. Term frequency, slightly more complicated. This actually is a variation really on the term occurrences, but it normalizes the value so that it's always between 0 and 1. And RapidMiner uses a square root of the sum of the squares as the normalizing denominator. We'll see that in detail. The important point about term frequencies is that the value depends only on the terms within a single document. This is in contrast to term frequency inverse document frequency, which I shall refer to as TF-IDF, which is more complicated. It reduces the values of terms that appear in many documents. In other words, it doesn't restrict to an individual document. It's been shown to be empirically useful. It makes sense. Words that appear in lots of documents are less likely to be predictive of class. So making them less important by giving them a lower value is a sensible way to proceed. And obviously the converse is true. Words that appear in fewer documents are empirically more predictive. Hence, give them more value. The formula is more complicated. It's basically the term frequency multiplied by a log of n over n, n being the number of documents in total, that's the big N, and little n is the number of documents in which the term appears. And there's also a normalizing step. And when we get to the worked example, we'll go through that in detail. So now let's look at the worked example. So this is the crib sheet that I'll follow when we bring up the RapidMiner process. We'll simply go through the different types of methods of creating the word vectors, and these words here really just give us the detail. So what I'll do is I'll bring up RapidMiner and just work through these notes. So here's the process. It's called word vectors. It's very straightforward. It creates a very simple set of documents. Let's briefly look at one here. As you can see, this document is "The cat sat on the mat on the plane." Strange, meaningless sentence. The second one is "The rain in Spain falls mainly on the plane." And the third document is "The cat, the mat and the rain are in Spain." Fair enough. Anyway, all that's going to happen is that we're going to do some processing inside this loop here, and the resulting example set, well, let's run it and you'll see. So what you're seeing here is, for each of the documents, I'm doing different word vector creation techniques for each of the documents. If I sort this column here, doc1, you can see that I've done each of the four vector creation types here, and I've included the text so you can see what's happening there. You can see this is the length of the document, and here are the attributes that are resulting from this, and we can work through these one by one. Let's start with the simple ones. So binary term occurrences and term occurrences, they're very straightforward. And you can see the cat sat on the mat on the plane. Basically, for the binary term occurrences situation, you can see each time that word appears in the original text, an attribute is created and it's set to the value 1, cat. So it's there. The appears 3 times, but the value of the is set to 1 in that situation when it's binary term occurrences. In contrast, term occurrences actually counts the number of times each word appears. So you can see the appears 3 times and on appears twice. So far so good. For the term frequency case, you can see here that there's a normalizing factor has been applied to scale this between 0 and 1. In RapidMiner's case, the normalizing constant is the sum of the squares of all of the term occurrences. The square root of that is then used as the denominator for the normalization step. So, in other words, 1 squared, 2 squared, that's 4, another 1 squared, another 1 squared, and 3 squared. The sum of those is 1 plus 1 plus 4 plus 1 plus 1 plus 9, which is 17. The square root of 17 is then divided into the term occurrence. So I would predict then that this value here is 1 divided by the square root of 17, and we'll do that quick. Here's a calculator. So the square root of 17 is 0.2425, and because the term occurrence is 1, then it's just 1 times that. So you can see there, sure enough, that's the square root of 17. That's also square root of 17. This one is 2 times 1 over the square root of 17, and this one is 3 times it. And you can repeat the same thing for the other documents. This one here, you can see that the denominator will be 1 plus 1 plus 1 plus 1 plus 1 plus 1. So 1 to 6, 7, 11. 1, 2, 3, 4, 5, 6, 7, 11. It should be the square root of 11. So I'm predicting the square root of 11 divided into 1 will give that number there. Let's see if that's right. .3015. Yep, I'm sure enough. That's good. And so on. We could do the rest. So the point about term frequency is that it's normalized between 0 and 1, in contrast to term occurrences, which can get very big indeed. So if you've got a large corpus with hundreds of words in it, then these numbers will get very large, and some classifiers will struggle. And of course that's partially solved by the binary term occurrences approach here, but the trouble with that is you lose precision, because there's really you can't tell the difference between the and cat. The is more common than cat, and by making it just 0 or 1, maybe that's losing something vital. So finally, for the TF-IDF case, we'll explain where these numbers come from. I have actually done calculations to recreate these numbers, but it's rather involved and will detract from the main message. But basically what you do is you calculate the term frequency, and then, so for cat, there is 1 word cat in the entire document, and you normalize that by the number of terms in the entire document. So you basically 1 divided by 9 in this case. So that's the term frequency part of the calculation. Then what you do is you multiply by a log of the number of documents in total, which is 3, doc 1, doc 2, doc 3, divided by the number of documents in which the word cat appears. And we can see by examination that cat appears in doc 1 and it appears in doc 3. So therefore, the factor that you multiply the term frequency by is the log, the natural log of 3 over 2. Having done that, you get a value, and then you repeat that for all of the other ones. And then what you do is you square those values and add them up and take the square root, and that becomes the normalizing constant that you divide into the original TF-IDF calculations that you are maintaining, and that will then give you these numbers here. But the key point really is that you can see that here's an example of something that appears in 2 documents out of the 3, compared to this one which appears in only 1 document out of the 3. And you can see that the value for this attribute is higher because the word appears in fewer documents, and so the inference is, the assumption is, maybe it's more predictive of the final label. And you can also see that the word the, which appears in all 3 documents, is set to the value 0, because obviously it appears in all of them, so therefore it's very unpredictive of the final class. And you can sort of see why that mathematically, if you do the log of 3 over 3, which is 1, when you take the log of 1, that's always 0. So when you're multiplying the term frequency by the log factor, which is 0, you get 0. Hence, words that appear very commonly tend to have low values, and if they appear in all the documents, it's 0. If they're rare words, they'll appear more often. And obviously that is intuitively sounds like a good idea, but of course it does depend on the problem whether it really works. So let's apply these things to the original spam and ham classification process. So I'll bring that up. Here it is. You may remember it from the initial video. Basically, we get some training data, we build a model, we estimate the performance on that, we then get the test data and apply the original model and see actually how we did. And what we'll do is we'll compare by changing the vector creation method here in the 4 cases, and I'll start with term occurrences, make sure that they're both the same. Yep. So if I run that, we'll see what the answer is, and then there's a table. I've written it all down previously, but you can see it actually running now. I'll pause while it runs, it takes a few seconds. So it's finished. So in the term occurrences case, it got that as the 913 spams predicted that are actually ham. So that's the bad problem, and there are 93 spams that got through to the inbox essentially. Let's repeat that now. Let's change that to be binary term occurrences. Run it again. I'll pause until it's... So here we go. Now you'll notice it's got worse. An extra 100 have been inaccurately classified here, whereas in this case there are some about 30 fewer, I think. Let's repeat it again now for term frequency. Again, I'll pause until it's done. So here's the answer. Now we notice it's got better, 771. So that's an improvement from the term occurrences case actually. And it's got a bit worse on this case, but the one we're really interested in is this one here. And then finally, let's go back to, let's do TF-IDF just to see if that makes even more difference. I'm running it again. I'll pause. Here's the answer. So it's actually a little bit, slightly, marginally worse than the term frequency case. So that's all very interesting. Let's bring up a table with those in. So those are the numbers. And you can sort of see that term frequency is best really, and binary term occurrence is the worst. It's a bit of swings and roundabouts, but term frequency scores better here, does slightly worse here than the term occurrence, but overall term frequency is the best. And it's likely to be actually because term occurrence is not normalizing the terms, and the binary version of the same is actually losing information. So it's sort of not surprising that with large corpuses and large numbers in the term occurrence case, then we're seeing slightly worse predictions. TF-IDF doesn't perform the best, and this could be evidence that common words are in fact needed. Now there's a later video coming where we'll look at pruning, which may help with this, but anyway, for now we can certainly conclude that term frequency is a worthwhile thing to look at, which points to making sure that you normalize the values within your word vector. So we'll just summarize now in a final slide. So what we've done is we've looked at some details of word vector creation, and there are different approaches: binary, term occurrence, term frequency, TF, IDF. And hopefully you've seen obviously the details of how they go about what they do and what their strengths and weaknesses are at a high level, and you've seen also how we've applied that to the spam and ham classifier, and we've seen that term frequencies seems to be the best in this case, which is actually not surprising. So with that, we'll close there.